I will also record this. Okay. So let me go through again. Sorry, I didn't share this now. So 1.1 and 1.2 class is good to read through. Method of neutral equilibrium is the method, one of the methods that we can make use of to determine critical load. And we will see in this later on using examples of Euler column and other columns to show you the process of derivations of the governing differential equations, what is Euler column, the assumptions, and also eventually how do we get the solutions. That is, what is the critical load of Euler column and what is the buckling mode associated with the critical load. Then we will talk a little bit about the important behavior of Euler column that we can understand from these derivations here. And then we will go to column with other kind of boundary conditions, different from Euler column. So what is the corresponding critical load? So from here we can see the effect of n conditions of the column on the critical load and also the associated buckling mode. So there will be three classical boundary conditions or n condition of the column that we will go through. And eventually from this, we see again the process of derivation of the governing differential equations, the process, and how the concept of neutral equilibrium is being used. So let me start with this, the first one, Euler column. Okay, we are going to go through the process of derivations of to determine what is the critical load of the Euler column. And at the end, I think you will see that that equation is what you're familiar with. Okay, so let's go through this. So critical load of Euler column. So Euler column class, it is named under the person who contribute, I think, quite a lot in stability of column theory. So Euler, this is the name of a person. So Euler column, sometimes we call it Euler. So you can produce Euler or Euler, but I will use the Euler column. Then shown in this diagram here is a column, straight one, with one end pin, and the other one also pin, but able to move in the axis directions, subjected to a dot P here. And the height of the column is L, and the bending rigidity of the column here is EI. So it's made of materials with modulus of elasticity E and with section properties represented by moment inertia I. So first, I define what is the meaning of Euler column, right? So that you can understand. So Euler column is an idealized, ideal column, which is prismatic. Prismatic is the cross-sectional area are constant all the way from the top, from one end to the others. Cross-sectional area is constant. The materials is homogeneous along the length of the column. So everywhere the material properties is the same, homogeneous. And then both ends are simply supported, which means it can rotate, but it cannot move left to right. So lateral translation is restrained. Rotation is not restrained, it is free. The Euler column, both ends are simply supported or pinned like this. Of course, here, in order to simulate this loading, so we have this able to move up and down, but important thing is cannot translate left and right, but allowed to rotate. At the other end also cannot translate left and right, but can rotate. Member is perfectly straight. It's another thing. It is an ideal perfect column, which later we'll see This is never happened in the actual column, but for derivation of critical load, we make everything perfect. Member is perfectly straight. Load P is applied along the centroidal axis, no eccentricity, which is again never happened in actual column. But for Euler, we make that assumptions. And we restrict this to linear elastic material. And Hooke's law is obeyed. That is, strain is equal to E multiplied with epsilon E. So you have a linear stress-strain relationship. And also we restrict ourselves to small deformations. Small deformations when you talk about Euler column. So in this case, we can approximate the curvature. We can approximate the curvature to be approximately equal to y double dash, or y double dash is equal to, this is actually d2y dx2. Okay, where later we see x is pointing in the axis direction of the column and y is pointing perpendicular to the axis. So that is x and y, and then the deformation of the member is small, so that curvature can be approximate using this relationship, which is y double prime, which is a short form for d2y dx2. So second differentiations of y. So this is the assumption make for an Euler column. Okay. Now, here is the free body diagram. Here is a diagram showing, this is a diagram showing the column which is originally straight here. Originally straight, represented by this dotted line with height of L and then bending rigidity EI. And shown here, the solid line here is what we call the slightly bent configurations at neutral equilibrium. So class, for methods of neutral equilibrium, the first thing that we have to do is we have to sketch this. We have to approximate this sketch, which is the slightly bent configuration at neutral equilibrium. So this is actually slightly bent only, but this is drawn in a highly exaggeration manner. Okay, we magnify this many times. This is actually representing slightly bent configurations. But if we draw it slightly, then we don't see anything, so we magnify it many times. Okay. So the important thing here that you should take note is to use method of neutral equilibrium. So you have to start with approximating this curve representing the slightly bent configurations of this column at neutral equilibrium. And this one must reflect correctly the boundary conditions here, which is it cannot translate in y directions. This is a y, this is a x, but it can rotate. Same for the top and the bottom end. So this is the first thing that's important when we use method of neutral equilibrium. What is the shape of the slightly bent configurations at neutral equilibrium? So this slightly bent configurations is the equilibrium position which is possible at neutral equilibrium together with the straight one. Remember again, class, at neutral equilibrium, there are two equilibrium positions which is possible, the straight one and the slightly bent one. So after we do this, the next thing that we do is we have to, so this is the first thing that we do in deriving, try to get what is the critical load using method of neutral equilibrium, using the concept of neutral equilibrium in this method, and this is called method of neutral equilibrium. So the second thing that we have to do is we have to get the equilibrium, moment equilibrium equations using these slightly bent configurations. Using these slightly bent configurations, we cut it out. We cut it out from here and we take one part of this and we draw here. So this is a free body diagram cut out from these slightly bent configurations at neutral equilibrium. And here we show all the forces acting. And because this is bent, so we have bending moment acting on these cross sections. And here you have P acting here. So for equilibrium, you should have P also here. And again, our coordinate axis is X is here, Y is here. So here, the location of this section is X from this end. And the deflection of this section X is Y. Now, from the theory of beam theory, we can relate the bending moment here to the curvature, assuming small deformation by this relationship. M is equal to negative EI Y double prime. So this M is assuming as a kind of sagging moment. And under this coordinate system X and Y, then we have this relationship M is equal to negative EI Y double prime. So after that, to get the governing differential equations based on this slightly bent configuration, the free body diagram, we just need to take moment at this point. You take moment of all the forces at this point here, we make it equal to 0. So we get this one minus this, take moment, this one, minus this. Okay. So we get minus EI Y double prime minus PY, and you make equal to 0, you simplify, you get this. So this is what we call the governing differential equation for the slightly bent configurations. So once we get this, so in order to get to the P critical load and also the associated buckling mode, then we need to know how to solve this. So this is a second order. This equation is a second order because you have differentiation 2 times, ordinary differential equations with constant coefficient. So we need to know how to solve this kind of equation. Second order ordinary differential equations with constant coefficients. So there are many references that you can refer to. There are also many YouTube and on the internet explaining about these second order ordinary differential equations with constant coefficient, how to solve them. So it is good that when you have the time, please go through this. Okay, we will only point out the important things that you need to know. Okay, when we try to solve this in the solution process. But why it is like that? I think please you have to go back to the basic about second order ordinary differential equations, especially with constant coefficients. So this governing differential equation is EI Y double prime. EI is the bending rigidity of the column. P is the actual load applied. Y is the deflection. Now, in order to solve this, let me go to the detail. Okay, let me go to the detailed process here. Going to refer to this. You can read through all the necessary, very detailed process again here. Okay. So we first reach to this, as I show on the slide, EIY double prime plus PY. Okay. Now there are some assumptions which has been made to arrive at these equations, but if that assumption is not made, then these equations will become more difficult to solve. Okay, so these are the explanation here. You can read through. So important to take note what are the assumption which has already been made here. Here it explains about what if the assumption is not valid. So the equations here become more complicated to solve. So this is a linear differential equations with constant coefficient, second order. Okay. Because it is a second order ordinary differential equation with constant coefficient, EI and P here. So the solution is quite easy. Okay. But please take note of the assumption that we make when we derive these equations. Now, in order to get the solution to this, we change it into a standard form, which normally we see in ordinary differential equation, the theory of solving this. So we divide this with EI. Okay, we divide it with this with EI, and then we introduce these terms here, K square. So this term K square class is will appear many times in our subsequent lectures slides. So please remember the meaning of this symbol K square. So K square is P over EI. Okay, is similar to your omega square. Okay, omega square. Omega square is K over M. Okay? Omega square is K over M in your dynamics. So in stability, we have also something similar to omega square, which is important, K square. Okay, so K square is P over EI here. K square is P over EI. So K square includes informations about axial load, which is being applied, and that we want to determine what is a critical load, as well as the properties of the column, which is material properties and section properties. So once we introduce this, divide this whole thing with EI, so this equation can be simply turned into this form. And this is a standard form. Yeah, this is a standard form of ordinary second order differential equations. And the right-hand side here is 0. So similar to the case of free vibrations, you have right-hand side equal to 0. So this is homogeneous linear differential equations. The right-hand side is 0, is homogeneous. Later, in other cases, we see the right-hand side not 0 anymore. But for Euler column, we have this governing differential equation, very simple one, and it is homogeneous, which is the right-hand side equal to 0. So the solution of this, I think we don't go through the detail. The solution of this for this y prime plus k square y, where k square is constant, is given by this equation here. Y is equal to a sine kx plus b cos kx. A sine kx plus b cos kx. So this is the homogeneous solution to this linear differential equation. So remember this form here, y solution of this. To find the solution of this means we want to find the y here, but there is a two constant here, a sine kx plus b cos kx. Remember k is square root of p over ei, or k square is p over ei. So we have two arbitrarily constant here, so we need two boundary conditions to solve this. So the boundary conditions, we have to go back to the assumptions made for Euler column. The Euler column has two ends. Both ends are pin. So what is the conditions of y? And what is the condition of y prime, the slope at this end here? So those are the boundary conditions that we need in order to determine what is A and B here. So that is the next step, to find the suitable boundary condition. So the boundary conditions here that we have is at one end here, bottom end, y is 0, at the top end also y is equal to 0. So we make use of these two conditions. Then we get first b is equal to 0. So when b is equal to 0, the b terms disappear, so y become only the term with the a there remains. Then again, make use of the second conditions here. Then finally we get from this to this equation. So these equations tells us A sine KL is equal to 0. And remember what is A here, class? Remember what is A here? A is the unknown coefficients in these equations. So these equations represent the shape of the slightly bent configurations. If the column is going to bend at neutral equilibrium, the column can stay in the shape of slightly bent configuration. So this is the shape of Y, okay? Which is, if I come back to here, this is the shape of Y here. And A in that equation, class, is undetermined. We don't know the A value, but we know the shape is like this. The shape is like this, okay, in the form of sine curve, but we do not know what is the amplitude, okay, but we only know the shape. So what to do with these equations is an important thing in the process of determining the critical load. And in order to finally get to the conclusion, what is a critical load, we have to understand the meaning of A. Okay. So A goes back to equation here. So A represents the amplitude of the slightly bent configurations. If A is equal to 0, then Y is equal to 0. Y is equal to 0 means, class, Y is equal to 0 means this curve is flat, goes back to the straight one here. Goes back to the straight positions. This is Y equal to 0. If A is equal to 0. Okay? If A is equal to 0 in the equations of Y is equal to A sine KX. If A is equal to 0, then you get Y 0. If Y 0 means you get the straight positions of this column. So if A is not equal to 0, then Y is equal to A sine KX, which is, it gives you the slightly bent configurations. So that is the meaning of A here, A0 or A not 0. Okay? Now, once we understand this, so we come back to this equation now. We have to make decisions now. So A multiplied with sine KL is equal to 0. So there are two possibilities for this to be 0. So this 0, if this is 0, then surely this becomes 0. Or if this one 0, it doesn't matter this A 0 or non-0. If this one 0, then this also becomes 0. So A sine KL equal to 0, it can means A 0. Then definitely this is equal to 0. And second one, if this 0, definitely this is also equal to 0. Now, which one we should use in order to make conclusion about the critical load? Now we have to look at if A is equal to 0 here. Let me go back to this. If A is equal to 0 means we get back Y is equal to 0, meaning that the straight one. Then if A is equal to 0, then this here, it doesn't matter whatever value that you get here. So K can be any value. If A is equal to 0, A multiplied with whatever value we here equal to 0. So it meaning that whatever value that you have here, it doesn't matter. So meaning that K can have any value. And if K any value means P can have any value. So P any value meaning is, if P any value meaning that this P is this axial load here. So axial load can have any value here. Okay, and it is still in equilibrium positions because the straight position is the equilibrium positions. So it doesn't matter P 0, P equal to 1, 2, 3, 4, p any value. So this equilibrium position is one of the solutions. So that is the meaning of this case. A is equal to 0. So if you read here, class, if A is equal to 0, K and consequently P can have any value. So this means that A is equal to 0 is a straight positions, and it only tells us that for the straight positions, any value of P will be the solution. And this kind of result, based on A is equal to 0, is known as trivial solution. So in study of stability of structures, we come across this term trivial solutions. Trivial solutions because it is a solution which is trivial, which is things that we already know. What we already know is for the column in straight configurations, okay, P, it is in equilibrium positions no matter what the value of P is. Okay? The straight configuration is the equilibrium solution, doesn't matter what the value of P is for the straight one. So this is, we already know, okay, which is the trivial solutions. That a column is in equilibrium under any actual load P as long as the member remain perfectly straight. So this is trivial. We already know. Now what we want to know, class, we go back to what is the purpose of solving this problem, is we want to know the critical load. So we want to know the critical load. So that's why in order to find critical load, this A is equal to 0 is not the condition that we should use, but we should use the second condition, which is psi KL should be equal to 0. So A is equal to 0 give you the trivial. It doesn't give you the critical load. So to get the critical load, you need to set this second one, psi KL is equal to 0. Then the solutions for psi KL is equal to 0 is any multiple integer value of pi. It can be pi, 2 pi, 3 pi, 4 pi, 5 pi. So any number of this is the solution of this. And once you find this KL, we substitute back into these equations here. K is m pi over L. Then we get the shape, the corresponding shape or the mode shape is given by these equations here. So this is the corresponding value of the P where the slightly bent configuration is possible. So the load, if you read here, the load given by 1.7 here can be in equilibrium in the slightly bent form. So any load here, the column can stay in the slightly bent form. And the shape of that slightly bent form is given by this. So there are many P value here and many possible shape of Y here, depending on the N value that we use here. N can be 1, 2, 3, 4, 5, 6. But in determining critical loads, we are interested in the smallest one. We are interested in the smallest value. So the smallest value corresponds to N is equal to 1. So if you choose N is equal to 1, so from equation 1.7, you get equation 1.9. So this is the critical load of Euler column, which is the famous Euler column. P is equal to pi square EI over L square. EI is the bending rigidity of the column. L is the height of the column or the length of the column. And you put N is equal to 1, equation 1.8, you get to this shape here. And you get the shape. The shape is Y is equal to A sine pi X over L. So this load here, class, is known as the Euler load. 1.9 here, P pi square EI over L square. This load is known as the Euler load. And what is the meaning of Euler load? It is the smallest load at which a state of neutral equilibrium is possible, which means the column can stay in both the straight one and the slightly bent one. Okay. So if I come back to this, summarize it here, whatever explanation in detail given in the book chapter that just now. So for Euler column, this is the shape of the slightly bent configuration at this particular Euler load or the critical load, which is pi square EI over L square. And this A sine pi x over L represent this curve here. It represents this curve here. Yeah? This one represents this curve. A is indeterminate. We do not know what is A. We do not know what is A, okay, but only we know that this shape is in the form of half sine wave. We do not know what is A here, okay? But we do know that this is in the shape of sine. So that from the derivation just now class, we see two important. We have some important information that we can get about the behavior of Euler column. Okay, behavior of the Euler column. So remember, Euler column definitions is pin at both ends, perfectly straight in the beginning. Is perfectly straight, and the loading is no eccentricity, perfectly zero eccentricity. The material is obeys Hooke's law, linear elastic materials, and the cross-sectional area is constant prismatic. Okay? And material is homogeneous. So this is the definition or assumption made in defining Euler column. So we see the Euler, the critical load is given by these equations, and the slightly bent configurations at neutral equilibrium, which is possible at neutral equilibrium, is given by these equations. So now, in order to understand a little bit about behavior of this column, which is perfectly straight, under the action of loading P, we look at this diagram here. Okay? This diagram here. So this diagram shows P versus A. Okay? What is A? A is appearing in this equation, A sine pi x over L. Okay? A sine pi x over L, which is this equation for this curve, the slightly bent configurations. So here is A and this is P here. So this diagram shows that for Euler column, which is perfectly straight, as long as the load P, if you keep on increasing the load P, as long as the load P is below this critical load, then the column will remain straight. The column will remain straight because this is the only possible, this is only the straight one is stable. So the column will remain straight. Now, if you increase the P, if you keep on increasing the P acting on these straight configurations, exceeding more than beyond the value of P Euler, then the straight one become unstable. So the only possible one is the bent one. Is the bent one. So beyond this, the only possible configuration, the only possible equilibrium position is the straight one, which is the stable one. And if more than this, the only possible equilibrium position is the bent one. Why? Because the straight one is not stable anymore if P applied more than this. Then at this particular point here, which we call the bifurcation point, corresponding to the value of P is equal to P Euler on this axis here, you have a bifurcation point. So at this particular load P is equal to P Euler, then this A can have non-zero. A can have non-zero value. Below this, not possible. A only 0. Above this, A only 0. Okay. So only here, at this bifurcation point, where the load level is equal to P is equal to P Euler, then you can have two solutions. You can have two solutions. One is here, which is A is equal to 0, the straight one. The straight one is A equal to 0. And because it can bifurcate, it can go in these directions. When you go in this direction, mean A is not equal to 0. So it can have this A. It can be in that equilibrium position where A is not equal to 0. So this diagram shows that at this P below P below this P Euler, A will remain as 0. Okay, and the only possible equilibrium position is the straight one. At bifurcation point here, then it's possible for the column to have two equilibrium position. One, the straight one, which is A is equal to 0, we stay here. And another one, when it goes in this direction, which is A is not equal to 0, which is a slightly bent one. Then if beyond this, I think the only possible one is the bent one. Okay? Is the bent configuration because the A is not stable anymore. Okay? The straight one is not stable anymore. The only that it has to get to the bend configuration. So this load here, the point on this P versus A diagram here is called the bifurcation point. And at bifurcation point, it means that there are two solutions at the situation where P is equal to P Euler or where P is equal to P critical for an Euler column. Okay. Now, these explanations you can read through again in this particular part here. Okay. This particular part will explain about the behavior of the Euler column, the behavior of Euler column. Up to Euler load, the column must remain straight. At the Euler load, there exists a bifurcation of equilibrium. That is, the column can remain straight or it can assume a deformed shape with indeterminate amplitude. We do not know what is the A value from these derivations. This behavior signifies a state of neutral equilibrium exists as Euler load. So Euler load is the transitions from stable to unstable. Below this stable, after this unstable. At this load, neutral, where two equilibrium position is possible. So now we have